everyone for joining this session, and thank you so much to Professor Kim for accommodating his very busy schedule to deliver this very professional talk. So the topic of the presentation would be prognostic and health management of composite structure using industrial AI. So just to give you an overview of Professor Kim's expertise, he receives his bachelor and master degree from the Department of Aerospace Engineering at Enha University, South Korea in 1997 and 1999 respectively. He earned his PhD degree from Arizona State University in 2003, where he conducted research supported by NASA Langley Research Center and the US Air Force Research Laboratory on smart composite modeling and computational structure analysis. Professor Kim is currently serving as full professor in the Department of Mechanical Robotics and Energy Engineering at Dongguk University, Seoul, South Korea. Professor Kim's research interests include prognostic and health management of composite structures, power plants, industrial robots, and mobility batteries. He is also interested in biometric actuators, adaptive structure, and structural analysis. He is also serving as director of the Brain Korea 2021 M Center at Dongguk University, Global Intelligent Robots Center, leading significant research initiative. Professor Kim has so far published 245 SCIE journal papers, achieving a tremendous H-index of 46 with over a very impressive 90,000 plus citations. His outstanding research contribution have been recognized through numerous academic achievements and awards from various academic societies in the PHM field. So I think we are honored to have you, Professor Kim, here for your presentation. And I believe you can share your screen and start the session.
Okay, thank you very much, Ashif. Let me share my screen first. Can you see my screen?
Yes, Professor, it's coming. Yeah, I can see it clearly now.
Okay, thank you very much. Let me start my presentation today. Today, I'm going to talk about prognostics and health management of composite structures using industrial AI. I think you might not be familiar with the prognostics and health management. It's PHM. So maybe I want to give you a brief introduction of PHM first. After that, it's application of composite structures and some other case study of this PHM. And finally, concluding remarks. The introduction of PHM. PHM, let me start with a simple question. What if machine could tell us and they are about to break down before they actually do? That's exactly what PHM does. PHM stands for Prognostics and Health Management. It's like a digital healthcare system for machines. PHM is an emerging engineering field that enables us to do two main things. First one is monitor the current health condition of a system in real time. And second one is predict its future condition under actual operating environments. In simple terms, PHM gives machines the ability to tell us, I'm fine now, but I might break down soon if nothing changes. A useful way to understand this is by comparing it to human health. This figure, we see a model how humans are managed when get sick. First, we detect the disease and analyze it, prescribe the treatment, and cure the patient. The same logic can be applied to the machines here, or robots here. We detect anomaly first in the system by sensors and analyze data and make predictions, support decision making, and perform timely repairs before actual failure happens. So in both cases, whether it's humans or machines, we are aiming for predictive diagnosis and proactive care. This comparison helps us see PHM not just as a technical system, but as an intelligent, health-oriented strategy for engineering assets. Let's now talk about why PHM is becoming essential, especially in the era of smart manufacturing. First of all, if you get the life cycle of a typical industrial system, you'll notice something surprising. Yeah, this is a pump system. And its initial cost is just 9% and installation cost is 8%. The other 80% is maintenance operating cost. So it's clear the managing the health of the machine is not optional. It's crucial. As we move to the Industry 4.4 era, where machines operate autonomously and deliver services, we need to ask who will take care of these machines. That's where PHM comes in. We are experiencing a paradigm shift in operation and maintenance. From old strategy, it was fail and fix, to the new approaches, predict and prevent. Instead of waiting for breakdown to happen, PHM allows us to say one step ahead. Here, over the years, maintenance strategies have gone through a major transformation. In the past, maintenance was mainly reactive. We waited for something to break down before fixing it. But now we are moving toward to proactive and predictive approaches, thanks to technology like PHM. There are 4 key types of maintenance strategies shown in this chart: corrective maintenance, preventive maintenance, condition-based maintenance, and predictive maintenance. And here, corrective maintenance is this is the traditional fix it when it breaks method. It's passive and often results in downtime and higher costs. Preventive maintenance. This is scheduled maintenance done at regular intervals. Even if the machine isn't failing, you still inspect or replace components. It's more active, but still not optimized. Here, condition-based maintenance. This approach only performs maintenance when necessary, based on the current conditions of the machine. It's predictive, but still doesn't tell you when the next failure will occur. Yeah, predictive maintenance. This is where PHM really shines. It uses data and models to predict when a failure will happen, so you can act before it does. So as you can see in this diagram, we are moving from high cost and reactive strategy on the left to smarter and data-driven predictive methods on the right. And at the center of this transformation is the PHM. Okay? The key enabling technology that helps us implement both CBM and predictive maintenance. To reduce maintenance costs while keeping reliability and safety, condition-based maintenance is a more popular approach. But to make a CBM truly effective, we need prognostics, the ability to predict how and when failure will happen. If we can predict crack growth or degradation in advance, we can schedule the right maintenance at the right time. As this graph shows, to match preventive, let me see, to match preventive maintenance case, the maintenance cost increased. Also, too little maintenance case leads to the expensive repair cost. So in between, there is optimal point here. This enabled the predictive maintenance. So PHM helps find this kind of balance. Let me see. A key goal of PHM is predicting remaining useful life, which is called RUL. This RUL means how much useful time is left before a component fails. The process starts with the data acquisition and using sensors that detect stress, vibration, or cracks. In this example, sensors attached on aircraft and monitors the degradation of the system. And this right figure shows the number of cycles with the degradation level. Based on the domain knowledge, there can be some threshold, And if the duration level fast specific threshold is meaning of end of life. So the prediction of this end of life is usually based on the statistics. And the current stage of the life here, duration level here, and if we can predict this end of life, then maybe we can predict the remaining useful life based on the probabilities. Yeah. I think RUL prediction allows us for smart decision and pure surprises. So this is the one representative example of PHM applications. F-35 fighter jet. So F-35 fighter jet introduced the first concept of PHM here. In avionics onboard systems, there are different types of system propulsions, structures, or mission systems. All of these sense data are collected in this AV PHM. And this one is going to the health management reporting systems, and it can show the current health status of this fighter jet. And during the flight or after landing down, the all data are gathered in the central systems, autonomous logistics system, of for the PHM systems, and it provide the troubleshooting of the fighter jet, and also it can provide information for predictive maintenance and the decision support of the maintenance. So this enables fast data-driven maintenance even before the jet land down. The F-35 shows how PHM can make a high-performance system smarter, safer, and more efficient. Another application of PHM is this 2.2 megawatt wind turbine system. The vibration data can be collected from the wind system, and the health indicator can be developed by the machine learning. Then maybe the algorithm can provide what is RUL. For this example case, before 10 days earlier, the failure, this system can provide the RUL. Another PHM application is this kind of fan engine. 4 different engine cases were monitored here, and fault indicators show the degradation trend, and the RUL was predicted for each case. This helps schedule the maintenance before the engine failure. So engine is critical component of modern commercial aircraft. So PHM technologies is now inserted in the monitoring of turbine engine. Another PHM application is lithium-ion battery. This PHM detects early anomalies and predicts life declination like this. This result shows this case the degradation prediction at least 3 months is earlier than it happens. This shows the basic composition of the PHM technology. PHM combines the sensor signals with the domain knowledge and AI. So industrial domain knowledge and combine of artificial intelligence with the industrial domain knowledge is called industrial AI. So this industrial AI can provide the prediction of health state of the system. To do that, from the multivariety of sense signals, the user can extract the features. Which feature can help the health classification of the system. Based on these classifications, we can predict the health state. So this animation video shows the key idea of a PHM, domain knowledge PHM. This is a component, bearing component, and usually this bearing is monitored by the vibration signals. And the bearing can be normal, warning, or faulty case. In normal stage, the vibration signal looks very clean. And we can convert this vibration time domain signal to AI domain. Then maybe it can, it looks like this. So we are saying this is a normal domain. Then maybe we can, based on our domain knowledge, we can consider this kind of health index. And the health index indicate if green zone, then maybe we can say this is normal or safe system. But if there is something happens, or some damages inside of the bearing, the time domain data provide this kind of some different patterns, right? And the different pattern, if we convert this to AI domain, then the previous data is located here. And based on this, we can make, if we make a health index, it's moved to orange zone, then we can say this is a warning zone. And as time goes by, aging, more aging, then maybe if there is fault inside, then the sense signal has complicated vibrations inside. If we convert this to AI domain, then the data is located here. Then this is the faulty zone. If we make this to health index, it's located here, red zone. Then we can say, oh, this is now something happened in bearing. We need to change it. So this kind of process is called domain knowledge-based PHM. Okay, to do PHM, maybe we have 4 main procedures of PHM. From selecting to the target to AI-based PHM modeling. The first one is target selection. First, we need to define target asset, like a robot or car or wind farm. Then we need to identify what is a failure mode, a component failure or a quality iteration, process problem, something like that. Understanding of this kind of failure mode is essential to selecting appropriate sensors and analysis methods. Second step is sensor data acquisition. Once we know what to monitor, we need to choose right sensors, flow sensor, vibration sensor, or thermocouple sensor, and so on, right? After that, we also need to decide where we need to locate this kind of sensor to obtain proper sensor data. Also, sampling rate is also a big issue. These choices directly affect the data quality and the fault detection sensitivity. After you get the sensor data, we need to extract the pictures. So raw sense data is not used directly usually. We need to first extract health-related features from time domain data case, maybe RMS, variance, maximum, something like that. We need to analyze which feature clearly separate from normal versus fault conditions. The raw, let me see. This one shows the example for health data 1 and health data 2, and classify the data is warning or failure or safe, right? So this kind of AI domain decision can be determined by AI-based PHM modeling. Here we use machine learning or deep learning. We need to choose it. We need to decide. So most common famous machine learning algorithm is sport vector machine, or deep learning is CNN, RNN, autoencode, and so on. So these kind of AI model can provide us a health index or to predict RUL. So this entire PHM pipeline, from sensors, target selection to AI-based PHM modeling, must be carefully tailored to the system being monitored. Every decision along the chain affects the prediction accuracy and the maintenance outcomes. So first step is target selection. I'll tell you step-by-step details a little bit more. So first step is building a PHM system. First step for PHM procedure is to identify what you want to monitor. This means the target systems. And if you decide the target systems, you need to figure out what is subcomponent, gears, bearings, pulley, or relays, and so on. From here, maybe you need to figure out what's related failure mode, mechanical failure, where, and so on. Here, if you know your system, then you know how it fails. So this slide explains the target selection step by showing the full failure chains from system to failure mode. For example, for the car, maybe there can be different subcomponent gear, bearing, and so on, right? And maybe this bearing failure might be, maybe there can be mechanical fracture, gear case mechanical fracture. And what is cause to failure? Maybe might be overloading. Then what is the result? Its result can be the car breakdown or quality degradation or even the work injury. If you decide your targets, then the second step is you need to decide how can you get the sensor data. So next, yeah, which sensor you need to use to detect the system? And for example, mechanical fracture to contaminations, maybe we can use thermocouples to acoustic emission or ultra sensor. So each sensor has different sampling rate. Imagine also different physical quantities. So low sampling rate case, small amount of data, but in long terms. But high sampling rate case, maybe large amount of data in short terms. If you get your low sense data, you must do the data pre-processing. Every sense data must have a noise, so you need to denoising the sensor data. Also, you need to convert your sense data to time domain data to prefix domain or time prefix domain together. Good sensor setup and clean data are critical for accurate patient modeling. Next one is feature extraction. So industrial sense data often has very high resolutions. For example, this kind of vibration sensor, it has 6.4 kilohertz sampling rate. For if 5 sensors, if you measure for 60 seconds, then just one measuring case, it provides you almost 2 million dimensions data point. If the raw data is too large and noise, then maybe it cannot provide accurate prediction or accurate modeling of PHM. So what we need to do is we need to do the feature extraction. Feature extraction case maybe usually converting the waveform into the meaningful values like RMS, kurtosis, or frequency band, something like that. After that, we need to choose what kind of feature is useful for our patient modeling. And also, the size of data is too big, so we need to do some dimensional reductions, which simplifies data without losing critical information. So these steps boost learning speed and improve patient model accuracy. So if you have good features, then maybe you will get better predictions with less computations. This is common data types. So energy-based or waveform. For its energy-based case, usually maximum, minimum, mean value, RMS, something like that. For example, RMS case maybe provide you average energy over time. This waveform case, maybe shape factor, class factor, impulse factor, provide you the shape of the data. So choosing the right feature type is critical for distinguishing healthy and faulty stage accurately. Another feature, common feature is this data distribution. So variance, skewness, kurtosis. Variance means how wide the data is distributed. Skewness means what's its distribution from the standard size. Kurtosis means how peaky or how flat compared to the normal distributions. So these kind of features help detect abnormal patterns, like sudden spikes or asymmetry will give you the early failure information. So next step is dimensional reductions. For this example, so I have 3 cameras for one image, but each camera provides you different information, but it's also for the one image, right? So there can be some redundancies. Same to sensors. Different sensors inside here, but it's for measuring the same information of the system. So question here is how to reduce the redundancy of the system. So if you reduce the redundancy, then maybe you can improve the learning efficiency and model performance. So in PHM, less can be more. So if you reduce dimensions wisely. So the most common dimensional reduction method is principal component analysis. Yeah, principal component analysis. It's called PCA. PCA finds a new axis based on the distribution of sense data. So new axis is called the principal component. So it's called principal component analysis. So it transforms the data from the original pictures here, maybe A, B, C axis to the principal components ranked by importance. In this example case, I have A, B, C 3 features, but if I'm using the first principal component, then maybe I can use just first principal component data only. Then maybe PCA reduce noise, and also it compress data and helps improve the model performance in PHM. PCA not only reduce dimensions, it also helps the visualization of data, compression, and anomaly detections. This X1, X2 is data is correlated and is distributed here. But if you find it's a principal component, if you put in the principal component actually transform to principal component data, then the data is clustered this way. Then it's easy to classify the data. So PCA simplifies data while preserving the key variations needed for PHM modeling. Next key feature extraction methodology, time frequency transformation. Usually the sensor data is time domain data, but the time domain data is not enough to provide us the information for damages. So if you can convert it to the frequency domain, sometimes it's helpful. Or if you are using time and frequency domain simultaneously, sometimes it's better. So we need to transform this kind of data to frequency domain or time frequency domain. The most common popular method to time domain data to frequency domain is short time fast Fourier transform, STFT. If you have a time domain data, you make a small windows, and if you do Fourier transform, then you are going to get time and frequency domain simultaneously here. It's called short time Fourier transform, fast Fourier transform. So this is an example of that STFT, time domain data converting to frequency domain by Fourier transform, or you make small windows and also make a time domain, frequency domain together simultaneously. Another way to extract to present the time frequency domain is called the continuous wavelet analysis, CWT. So CWT provides the different window. So high frequency data case, you can use small window. So long-term low frequency data case, you can use big window. So CWT case, you can use the flexible window size. Then maybe you can make a more fine grained insight for maybe complex signal behavior. So finally, AI-based patient modeling. So for the patient modeling, we need to use AI. So let's briefly see what's AI and the machine learning. You know, most of you know, right? Just briefly summary of this AI. AI is artificial intelligence is the broadest term, right? It's a system that acts like intelligent agent. That's AI. And inside of this AI subdomain, there is machine learning. This machine learning is the system that learns from data to make decisions. So inside of this machine learning, there is deep learning. Deep learning is a further subset, and usually using a neural network to automatically learn features from raw data. In PHM, the difference between machine learning and deep learning is machine learning case, we need to do the feature extraction by manually. But deep learning case, you don't need to do feature extractions. The deep learning algorithm itself do the feature extraction and classification. So thanks to the modern GPUs, deep learning takes much longer than the machine learning, but thanks to the modern GPUs, deep learning has become practical and powerful for real PHM systems. So here the most common representative machine learning algorithm is spot vector machine. Spot vector machine is determining the hyperplane using spot vectors. Spot vector means the separate line, and this spot vector is designed by these margins. So SVM, spot vector is widely used in PHM for fault detection and also classifications. Another common and simple machine learning algorithm is KNN. KNN is a very simple machine learning method. It checks which data point is closest to new one, and if this one is fault, and the new point close to this one is, we are saying, is fault. So to determine this one, KNN use the distance. Here in distance case, maybe there are maybe 3 different types of distance measurement: Euclidean, Manhattan, or Minkowski. So KNN is very easy and works well for basic classification in PHM. Another popular thing for PHM modeling is the CNN. The CNN is a deep learning method, right? It automatically finds important features and no need for manual extractions. It looks like there's convolution layer, Fullling layer, and it's repeated and fully connected and softmax. A convolution layer detects the patterns of the image, and the pooling layer makes it faster and it just make it smaller. This fully connected layer to the final decisions. So in PHM, CNN can be used for image-based diagnosis or vibration spectrograms. So CNN learns the features by itself, so which saves a lot of work. Another deep learning is autoencoder. So autoencoder is usually used for denoising or anomaly detection or dimensional reductions and so on. The summary of the full PHM process is from target selection to AI-based PHM modeling. Target selection is to choose the system and failure mode. And sense and data acquisition case collect time or frequency-based data. Feature extractions extract useful patterns and reduce time domains. And PHM modeling is use machine learning or deep learning to predict the faults. So each step is important to build a smarter and reliable PHM systems. So this is a brief introduction of PHM procedure. Now let's move on to the next part, PHM composite structures. We will look at how health monitoring techniques are applied specifically to composite materials. Yeah. Laminated composites are made by combining fibers and resins. Yeah. Right? And this gives them a high strength and flexibility in design. They are used in many fields. This is Boeing 777 figure, very famous figure, and more than 50% of this aircraft structure is now made by composites. Ships and cars and other structures also use the composites. So each layer of the composite, laminated composites, can be tailored to meet specific mechanical needs, like bending strength, impact resistance, and so on. This laminated composite has orthotric characteristics. Because of this, their failure mode is very complicated. The most common failure mode is 5 breakage, matrix crack, or delaminations. Among these, delamination is the most commonly happened. It weakens the structure and may lead to the catastrophic failure. To extend the life of the combined structure, it's important to detect this kind of delamination in early stage. To detect the damage of a composite structure, there are 2 main approaches. Well, first one is physics-based approach, and second one is data-driven approach. Physics-based approach uses formulas and material models like constitutive equations or fraction mechanics. It explains why the damage happens. Data-driven approaches uses sensor data and machine learning or deep learning to detect patterns and predict failures. It works well with vibration or acoustic signals. We often combine both to get accurate and reliable health monitoring. Okay. This is what I did during my PhD work. I analyzed how delamination affects the vibration behavior of composite plates. And experimentally, I measured the vibration mode of the composites and also developed a numerical model to describe the vibration effect of the composite structures. Based on these models, maybe it's published around 2003, my PhD works. Based on these models, I can develop the modal strain damage index and so on. This is a fourth problem, means I know where is the damage, and based on the damage, I developed numerical model to explain the damage effect. This result can help us to solve the inverse problem, means detect damage from the structural response. Around 2014, 10 years later after my PhD work, I did this kind of work. Based on my numerical model, I applied the random excitation of the system and get the random responses and do some system ID and instruct the system metrics, input metrics, and sense outputs. Based on here, using the system metrics and input metrics, I made the discriminative features and apply here to PCA, which I explained you before. And I plotted here two principal components. There are different 5 types of data. In time domain data, it's very hard to classify each classes. But if I use this kind of discriminative features, I can make this kind of different classes. So this was reported in computer structures. This means in time domains, it's not easy to distinguish the sensor signals, but if you choose proper features, then we can classify the data. That's the meaning of this work. After this work, year 2016, there was AlphaGo. AlphaGo defeated in PyGo, right? And after that, maybe AI is very popular in every engineering disciplines. And at that time, I also studied this machine learning, and it might be possible to apply to my field. So this we used a spot vector machine, and this spot vector machine, spot vector, can provide us the AI domains, different classes. So we report this one to Composite Structures, the top journal of the composites, right? And this Dr. Asif Khan, he did during his PhD work. So based on those studies, we found that this structural vibrations is global structural, it contains global structural information, right? But the damage is local structural information. So just time domain data is not easy to distinguish from to extract local information from this kind of global informations. But our previous work case maybe choose the proper discriminative features. It's possible to classify to extract local informations. But in this case, we need the input data, output data simultaneously. But in real application case, it's very hard to get input data. So question is it possible to classify this kind of damages using sensor data only? So the answer is yes. So we use a CNN here. We made the time domain data to this short time Fourier transform, and we made the image data, 2D array data. It's called image. And using this image data, we use the CNN and try to classify the damages. And it works. And it published in Composite Part B, the top journal, and in 2019. And this is more than cited more than 200 times. And this is one of the best, highly cited paper in my life. And also Dr. Asif Khan, he did this work. After this work, I realized, the damage detection based on the structural vibration is possible. So we tried to demonstrate this work by experiments. So we made the composite coupons using hot press. And this composite plate was cut by 300 by 50 by water jet, and we prepared 5 coupons for each, and we prepared the vibration the test system. It contains excitation system and the vibration system and the data acquisition system. This excitation system, we use the LabVIEW. What is LabVIEW? LabVIEw by PTC and provide the random signals. And this shaker provide the excitation of the vibration of the composite coupons, accelerometer gathering the data. So based on this experiment, we prepared the vibration data for the PHM modeling. So each case, we had 3 different health state, D1, D2, and H health case. For each health state, we have prepared 5 samples. So overall, we have 15 cases. For each case, we did 10 tests. So we had 150 signals like this. The whole data signal is we posted on our homepage. So maybe you can access this one in this link. But maybe you cannot access this PPT, right? So maybe what I did was I prepared this is our homepage, Smart Materials and Design Lab. So our research area, I have several different research areas. PHM is now my major research area. This PHM slide, I have PHM of combined structure, and I prepared the complete data set here. Some training code for spot vector machine and CNN, and also explaining PPT slide for this code. So if you are interested, visit my our homepage, and you can try to run the code. Anyway, based on these preparations, we developed some damage assessment method using AI. But one thing, the realistic issue is there is always, for the training, we need the balanced data, for which means maybe if I have a 3 different class, health, D1, D2, then I must have a balanced data here. But in real case, most data is healthy case, and there is no damage data available. So this kind of a case is called data imbalance. So this data imbalance cannot provide case results, the poor accuracy and the poor patient modeling, something like that. So what we need is then we need to make a balanced data. So here we use the data augmentation techniques. Dr. Ashif did this one, and he used our previous numerical model to make data augmentation. And yeah, without data augmentation, the prediction accuracy is very low. With the data augmentation, prediction accuracy is increased a lot, which means data balance for training is very important. So that's we discovered in around the year 2021, 2022, that time. So at this time, maybe Dr. Khan, he graduated, he got his PhD, and he moved our lab, right? So, and another PhD student, Muzamil, he is now research professor in our lab, and he took over Dr. Khan's work, and we developed another PHM models. We tried several methodologies. The first one is this one is we try to develop hybrid model to improve the PHM accuracy of the prediction of the composite damage. And here we developed a combination of CNN and SVM or CAE plus SVM. So CNN or CAE used to extract the picture automatically, and SVM used to damage classifications. So this kind of hybrid method case maybe can provide us, we can use both the strength of deep learning and the traditional classifier algorithms. So this is the result of hybrid methodologies. So we tested the several models. to compare the current results. So we use the spot vector machine, XGBoost, and CNN. CNN, the SVM also machine learning provided a good accuracy, 85% is not bad, but CNN provide better. But if you use CNN SVM or CAE SVM, the accuracy is increased. And CAE SVM case almost 99% accuracy, provide 99% accuracy. So this shows hybrid deep learning method can improve the damage classification accuracy and works well with the real vibration signals. Another one is to overcome that kind of data imbalance and also limited data case is using transport learning. So transport learning means we are going to use a very well developed model to our model. So our model case, may we have just very limited data, but if we are using very well developed model and if we use our own data for fine tuning of the well developed model, that means we can use both fine tuned model for predicting damage in our model. So that's called transport learning. And the result of here is maybe we use the well developed model means BGG16, BGG19, less than FA2 exceptions. This is all publicly available deep learning model. So if you use this one, then the prediction accuracy is increased a lot. That's what we observed in this study. So transport learning is also one good method to overcome the limited data case. Next study for to overcome this kind of limited and imbalanced data issue is using the data augmentation using GAN, artificial intelligence itself. Previous data augmentation is based on our numerical model, but in this case, we use the AI, GAN for data augmentations. So without data augmentation, I showed you, because of data imbalance, it's very hard to predict the damaged case. But if you use this kind of GAN modeling, and if you can make a synthetic data, so we have experimental data here using these small limited number of experimental data. If you are using the GAN model, generator made the fake signals and discriminator evaluate them, then we can make high quality synthetic data. So using this synthetic data and the real experimental data together for the developing the CNN model, then maybe the accuracy will increase a lot. That's what we observe. This is the flow chart, overall flow chart of that. And this is synthetic data made by the GAN, and it's compared to ground truth experiment data, and it's similar to each other, right? Based on this one, the classification accuracy increased a lot. So now here the accuracy, we use the same data, and now the health case is prediction accuracy 100%. Means this GAN-based data augmentation works very well. So another try is explainable AI. Most deep learning model case, the issue is black box. It's black box. The AI make the predictions, but the issue is we don't know why they decide that kind of things. Why did they make that decisions? So that kind of black box issue is sometimes very critical for the safety is a big issue. So recently, lots of people are trying to break down that kind of black box model. So people use develop this kind of explainable AI. Here we use the vision transformer model. And then this vision transformer can gave us some information which part influenced the decision of that AI. So to use the vision transformer, we use also scaleogram images, time domain data converted to scaleogram images, and here we use the patch level attention methodology, and this patch level attention model will provide the explainability of the decisions. So here, to show the explainability of our work, we compared another algorithms, yes, machine learning or transfer learning or another deep learning, and the vision transformer too. So accuracy is similar to each other. The deep learning case also high, less than high. The vision transformer also provide the high F1 score, but the other traditional methods, they cannot provide the explainability. But vision transformer can provide the explainability. Why they decide this one H class or D1 class, D2 class, something like that. So this is the explanation method. The patchy level, they have different levels of numbers. Then from these different levels of numbers, this vision transformer use the which part as their importance. And this analysis help us understand why the model made these decisions. To summary of our current work is like this. For data-driven PHM workflow is first we need to data collection, right, from sensors, and after that we need the data pre-processing, filtering, normalization, and formatting. After that we need to do some feature extraction. For machine learning, deep learning case, we don't need the feature extractions. So after that we need to do model selection, model training, model liberation, and if the model cannot satisfy specific accuracy, then we need to go back, and if it satisfies the accuracy, then maybe we can deploy for the monitoring of the systems. So this pipelines ensures the reliable, updatable, and intelligent page frame operation for composite structures. So this is I provide for you to understand the PHM of composite structures. I prepared two examples of our PHM of composite structures. First one is a machine learning approach, and second one is deep learning approach. So because of time limit, so I just quickly show you the how can you access this one. So as I told you in our lab homepage, you can find this page on composite structures, and you can download the slide for this two code, and there is the explanation of this code. This is just what I showed you, right? And from here, it shows how to use the code, the source code. So we have this time domain data. It's provided here, complete data set, right? And I provide two the PHM code for here. One is a spot vector machine, and the other one is a CNN. If you click here, it's not moving well, but it takes time. If you can, so okay. If you click here, it's a Python code, but it can run on the Google Colab. So you can see all the source code, and if you run the source code, then you will figure out how the PHM of a composite structure works. Okay. So because of the time limit, I cannot explain all the things. Maybe I can move to the next. And I prepared some other case studies based on the industrial AI-based PHM. So our lab also doing the PHM of industrial robot. And we did some project for the damage detection of the industrial robot. And the other one is power plant PHM. We also collaborated with Korea Electronics, and we also try to detect some leak of the pipeline of this 500 megawatt power plant. Maybe the details, maybe I'll just omit. And if you are interested, maybe I can share our papers. So because of time limit, just I conclude my presentation. PHM is a transformative approach enabling real-time health assessment and predictive maintenance of complex systems, particularly in composite structures and energy applications. Data-driven methodologies, including machine learning and deep learning, have demonstrated significant potential in detecting and classifying structural damage, even under data scarce and noisy conditions. Hybrid AI models, like CNN SVM or CA SVM, and explainable AI techniques improve interpretability and performance in real-world diagnostics. Robotics, maybe we just omit. We are currently advancing our research on industrial AI applications through ongoing collaborations with Hyundai Robotics for anomaly detection, and also trying to detect the RUL for lithium-ion batteries in mobility applications. So this is our current work for the real-time PHM technology development for composite structures. This is 5-year project and started from this March. And the previous work, we just classify damage only, right? But the real PHM, we need the RUL prediction. But RUL prediction is really difficult, especially for complicated structure. Right now, the very simple bearing, simple component, mechanical component case, it's possible to predict RUL. But this kind of composite structures, there is no paper available for RUL predictions. That's what we want to do is we want to combine physics-informed neural network and XAI to predict RUL. So this started in this year and 5-year project, maybe after 5 years, hopefully I want to develop some methodology to predict RUL of composites. Second one is the anomaly detection of robots. And third one is RUL prediction of mobility battery. Battery case is much easier than the composite structures to predict RUL. So this is what we are now trying to predict RUL of batteries. This is our current lab, and I have 3 research professors now, and PhD student, master student, and undergraduate students. I had 4 more PhD research professors before, but they left our lab last March. 2 of them went to the US. One go to the University of Michigan, the other one go to the Case Western University. So I'm trying to hiring more postdocs now, and our lab is also open to the world. I have lots of collaborators, and any kind of collaboration is welcomed in our lab. So if you are interested to collaborate with our lab, maybe you can contact me by email. Okay, thank you very much. This is the end of my presentation.
Yeah. Thank you so much, Professor Kim, for the very nice overview of the PHM, supported by very good case studies. So I think it's time to take some questions. So let me just go to the. We have one research scientist with us, Shauli. So Shauli, I can allow you can ask the question directly. I think it would be good to have an interactive session with Professor Kim. Yeah.
So can you hear me?
Yes, we can.
Thank you, Professor Kim. It's a really nice talk, really informative. Thanks for giving us this presentation. So I have a question regarding the specific case study for your machine learning to detect the delamination in composite structures, because I see that you are using the cantilever beam structure to generate this data set for training your machine learning model. So I'm wondering that because most of the time for machine learning model, it will be challenging for this kind of model to do the extrapolation. So I'm just wondering, is that possible for the well-trained model and apply this for detecting the delamination in some more complex structures, or just this model is only applicable for a specific case, for example, the same structure as the one you are using for generating the data set?
Thank you very much. That's very nice question and critical question, right?
Yeah.
The thing is, machine learning or deep learning model, their accuracy or their performance is based on the data set, as you know, right? So our previous work is just that's all the basic research paperwork, and their work. The importance of their work is, as I told you, from the global structural response. We can extract local information, damage information from the global structural response. And that's what we found and we reported in to the world, right? Using paper. And those is only applicable for very simple structure only now, because I have only the data that's for the cantilever structure only. So that's the reason I want to provide another things, physics model, kin, something like that. If we have more data for complicated structure, of course, I think right now the power of AI is I think good enough. So if we have enough informations, definitely we can detect damages for the complicated structure. But the issue is we don't have that kind of data yet. So if you have good data set for training, AI training, based on my experience, I can say I had several experience for not only for the damage detection for composite structures, for this lithium-ion battery and some robot, this kind of robot systems. If we have enough data, then definitely the AI model can detect the damage information. So the issue here is, do you have enough good data or not? That's the issue. If you have good data for complicated structure, definitely you can get a good model and you can develop a good model and you can predict damages. But if you do not have a good data, it's not possible.
Okay,
Yeah.
that's fair enough. Thank you, Professor Kim. Really nice talk.
So another good
Thank
thing
you.
is that's the reason we need maybe this field need the person like us, right? Engineers, because this problem is inverse problem. This is inverse problem, right? Figure out the damages from the sensor outputs. So that can be, it's really not easy. So here I didn't present today, but just today's presentation just have the classification of damage only. But what recently what I'm doing is what I'm doing with my student is localization of damage. So using the sensor outputs, we want to figure where is the location of the damage. Okay, so that's usually used in the structural health monitoring people did, right? But the issue is previous structural health monitoring case, the localization of damage is possible for very narrow zone, but we want to detect damage in very large structure, like this aircraft wing. It's very big one. A small area, it's possible to localize damage using RAM wave, something like that, guided wave, something like that. But it's not possible to use applicable to the big structure. So that's the question, and we want to try to develop some methodologies to localize damage. That's another level of problems. Classification of damage is very easy, but localization of damage is very, also maybe if you can class the severity of damage, also another issue. So there is a long way to go for in this field, I think, in PHM of
Yeah. I totally agree with that. So just like firstly, we want to classify if there's damage or not, then we'll move forward definitely to get a more accurate prediction for the severity and location for the damage, and yeah, more importantly, for much larger or complex structures. This will be for sure. It will be more challenging, but I agree with Professor that there's still a long way to go for this. Thank you.
Yeah, one thing is I heard as from Asif, and now you want to study the damage detection of a composite pipeline, something like that. Right now, this is one example of my work, and I collaborate with Hyundai Robotics. They also made many types of robots, and their robots are in the Hyundai automobiles smart factories. 100 robots inside of the smart factories, and if one of the robots stop, then the overall the process just stopped, and the huge amount of downtime cost occurred. So now they want to develop the PHM model like what we are talking, right? But this big company also, they don't have a PHM algorithm itself. So key of PHM is predicting RUL, but that's the last stage. So Hyundai Robot, they want to develop anomaly detection methodology now. So the overall the patient procedure, the first step is anomaly detection. After that, diagnosis of the system. Where is the fault? After that, maybe we can predict the remaining useful life. So still, this major company they cannot develop the anomaly detection methodology too. So only the I showed you the example of PHM, right? Turbofan engine. The gas turbine engine is a very important component in aircraft, and the GE or Pratt and Houston, the gas turbine engine, the makers, they developed the PHM technology, and they applying the PHM for gas turbine engine only. The commercial airlines, they are just using the PHM solutions provided by the maker, GE or something. But the maker, the GE asked too high cost, how can I say? It's too expensive. So also the commercial airline, they want to develop their own PHM algorithms. That's what we are doing now. And right now, there are lots of demands from industries for this kind of PHM methodologies.
We have maybe two more questions. So this is from Aldi. He says, thank you, Professor Kim, for the interesting presentation. I would like to ask for PHM of component from health to failure. How do we get the sensor measurement for different conditions? What he means is healthy, damage to failure. Do we need to test a component until failure and measure the response? If so, how would this apply to very expensive or complex components?
Yeah, the data is always the issue, right? As I told you, this Hyundai Robots and another the commercial airline. Right now, I'm collaborating with the Korean airlines, and they also want to develop their own PHM models. So the engine case, they maybe the GE or the engine maker, they provide the PHM solutions, right? So maybe, but they also want to apply this kind of methodology to other components, landing gear or structural part or other flight avionics, something like that. But the issue is here is everybody knows if they have enough data, easy to develop the AI models to predict the something, the patient model. But the issue is data. How can you get the data? And also, not just data. Maybe you must have labeled data. That's what you asked, right? If for the patient modeling, yeah, you need the good data. Good data means labeled data. For the patient methodologies, AI, what is it? Maybe here, maybe AI thing, blah 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 blah. Where is it? Anyway, there is three different types of AIs are here. Maybe supervised learning, unsupervised learning, reinforced learning, right? So reinforced learning or unsupervised learning is the best because they don't need high quality data, right? And they don't need unlabeled data. They don't need labeled data, but the issue is the actual the PHM model. Until now, still we need to use supervised learning. For supervised learning, we need the fully labeled data. Fully labeled data means for real applications, you should get a good quality of data, labeled data. But the issue is, I told you, there is always data imbalance. Most of data, your gathered data is healthy data, no damage inside. There can be some damaged data, but its number of data is much smaller than the healthy data. Then how can you balance the data? So for that, maybe you might need some techniques. Maybe, as I told you, data augmentation using AI or a physical model or transfer learning. You need to use transfer learning, something like that, right? That's what you need to do. But maybe just anomaly. I think your pipeline issue case, maybe the anomaly detection is in the beginning of the work. So anomaly detection case, maybe you don't need the labeled data. Just if you have normal data and that data might be, the methodology is different. What kind of sensing data is the issue? That's the first issue, but that's a different story. Anyway, as I told you in the beginning, right? Maybe you can use the resistance of the structure, electrical resistance as a sense data, or vibration, or something else, guided wave, something like that. But that's a sensor issue. After the sensor issue, if you have enough data, then maybe, and if you want to detect anomaly, anomality of the pipeline, means if you want to detect some damages, cracks or something, where something inside, then maybe in that case, maybe you don't need to high quality label data, I think.
Okay.
Anomality cases is the first step. So
I think we have one more question. It says, thank you for the nice presentation. Could you give a brief example on the use of RNN? I think he's asking about recurrent neural network for the damage diagnosis or prognosis. So specific example, I think he can search from your publications, specific example of the use of recurrent neural network for damage diagnosis and prognosis.
So my cases, I told you for my previous publication case, there is no prognosis. It's all related to damage classification, right?
Exactly.
So recent work is maybe damage localization. So for composite work case, maybe there is no prognostics, just all damage classifications. So no regression issue problems.
Okay, thank you so much, Professor Kim. And I think I will also request you for another session between me and you and the team. So we have some data set with us. I think after our taking consent from our director, we can share that data set. So usually we use this machine learning model for interpolation. What I mean is the model can only predict the data on which it has trained, or similar type of data. But what we also want to basically explore the capability of this AI for how much it can go for the extrapolation beyond the things it has seen previously. So we have very systematic data for that, and I can explain the data, and I think we can go for really nice publications together as a team.
Good.
Yeah. So I will request for a meeting through email, and then we can proceed for sharing the data and further developing the models together.
Good. I have a good research team, so maybe we can collaborate together.
Yeah. So thank you so much, Professor Kim, for your time and very nice presentation, super good insights into the PHM diagnosis and prognosis, and hope to see you in the near future as well.
Okay.
Yeah, thank you. Thank you so much and have a nice day.
Have a nice day.